All right, it's 10 o'clock, so we can go ahead and get started. Welcome, everybody, to this week's episode of the Long Coffee Break. My name is Bill Rohn, and I'm a sales engineer with Long. I really appreciate everyone's time. Thank you for joining us. Today, we get to talk about channel blending with blender products. We're joined by Travis Starnes. Travis is the business development leader for Blender Products. We are really lucky to be joined by him today. Travis, thank you for joining us. And with that, I'm going to turn it over to you.
Thanks, Bill, and thanks to the team at Long for the opportunity to share some information about our channel blender technology. For those of you who don't know about Blender Products, we are a locally owned business here based in Denver, Colorado. All of our engineering and manufacturing is based in one house, under one roof. We originally got our start in the 1940s under the entity of Rocky Mountain Sheet Metal Company. They started to experience temperature stratification in various air handling units for some of the jobs that they were a part of, from New Mexico up to Wyoming. And they developed a technology called the air blender that was used to combat stratification inside those units. They had such success with that they changed the name of the company to Blender Products in 1962. And so for a little over 60 years, we've been a small niche company that solved a niche problem within the HVAC space, and that's around stratification. So on this slide here is a few bullets around temperature stratification. There could be velocity distribution inside the plenum for uneven loading to the coil that could impact the performance of the coil when trying to remove water in the airstream, i.e. dehumidification, or uneven loading to the filter section. All those types of things we get involved with. The most common scheme for temperature stratification that we've seen implemented during cold weather events is a control modification. They changed the control scheme for that air handling unit. Some facility operators have admitted to reducing the amount of ventilation brought into the units during these times, or they prematurely abandon the economizer operations to trigger both the preheat coil to raise that minimum temperature above a freestat setting, and then they cool that entire airstream down to the desired set point. All that requires energy and ultimately just adds cost to the utility bill. So what we're here to talk about is another way to attack the root cause of temperature stratification and how can we enhance the performance of the air handling unit. So what you see here is a CFD simulation on the lower right. ASHRAE references, or lower left, ASHRAE references stratification. So I won't reference those sections in those materials. But what you'll see is outdoor air enters from the top, return air enters from the back in this particular case. This particular AHU has 44,000 CFM and a 25% outdoor air requirement. You can see the streamlines for each stream. They kind of bounce off each other and stratify inside that plenum. So one thing I wanted to point out is, contrary to some of the common practice out there, there is no orientation of outdoor and return air dampers in the mixing box that can effectively address stratification and promote effective heat transfer from one airstream to another. So the other thing I want to point out is, if you look at those particle traces of the outdoor air molecule or the return air, those may be traveling down the duct at 1,500 to 2,000 feet per minute or somewhere in that range. But the point being is they travel at a fairly high velocity, but once they hit that open volume inside the mixing box, the plenum velocity in that air handler can be in around from 300 to 600 feet per minute, depending on how the size of the unit. So the point being is that an air molecule, while it has little mass, has very little momentum. So trying to create a jet or a nozzle or some sort of collision in there to effectively shoot those airstreams at a distance can be a challenge. And especially with fan arrays inside air handling units, they tend to propagate this issue of stratification as it goes down the tunnel. So as one large air handler unit manufacturer in the US told us, they don't identify them as mixing boxes. It's more of stratification sections inside their air handler. The point being is true on site entry. I actually think the value proposition for mixing technologies is a little bit stronger on site entry units. And the reason for that is typically you can save a greater distance with our channel blender technology, and we'll get into why that is. But you can see here, getting that outdoor air across that plenum with an aspect ratio where the height is a lot less than the width, you can see that that's difficult to achieve. The channel blender was really born in 2015 We started doing a technology development exercise. And what we found was that a lot of the OEMs that we were talking to, and even some of the engineers, overwhelming feedback was, we like the mixing technology, but what we don't like with your static air blender is the additional footprint that it takes. So if you could develop a new technology that could provide effective mixing without the additional real estate, now you've got an area of the market that's underserved. Hence, the channel blender was born. We did not release this technology until 2018, after a couple of years of trial and error in our own lab, and then working with some other people in the industry. So this channel blender that came into the market was 2018. We think this is a new means to combat stratification inside air handling units. This product is used in the mixing box. It goes inside any mixing box, and it replaces the traditional outdoor and return air dampers. This mixing approach addresses the root cause as to why dampers in the mixing box fail to reduce temperature stratification, while eliminating one of the greatest penalties with using static mixers or other mixing technologies in the industry, and that's the additional extra tunnel length that those blenders or extra mixing technologies require. So how does it work? If you can imagine, in this particular isometric in the lower left, you would have dampers on the ceiling and the back wall. Those get removed, and those are integrated in an alternating fashion on the discharge side of that channel blender frame. That channel blender frame is sucked up tight up against the walls, buttoned down, and then you have alternating channels of return air and outdoor air that enter that module. The proximity of those channels create the opportunity for those dampers, which are in a modulating and control position. Those dampers would receive the same signal that they would normally receive in a normal operating unit. And so they would vary the percentage of outdoor and return air entering the air handler. When those damper blades are in a control or modulating position, they create a micro collision. And so really what we do is we promote transfer in a relatively short amount of time and a short amount of distance. So when I say short amount, if you look at that damper blade, we typically need around 8 to 12 inches downstream of that damper blade to raise that minimum temperature above a freeze stat. When we developed this technology, our original impetus for this design was to eliminate freeze stat alarms, or eliminate the detection of low temperature conditions. So that's what we started out doing, and now we're getting into applications where we're being asked, can you increase mixing effectiveness to enhance uniformity? And I'll talk about that in a few slides here. So let's take our base case. This is the mixing box that you saw previously in the previous CFD simulation. If you take that same mixing box and you integrate a channel blender inside that unit, we can raise that minimum temperature from 19 degrees Fahrenheit up to 46 degrees Fahrenheit. Now, there is no free lunch. We do require additional pressure drop to promote mixing. So we've raised the pressure drop across that mixing box from 0.15 inches up to 0.4. Now, I'd like to draw your attention to the particle traces of the outdoor and return air entering that channel blender module on the right. When those outdoor air molecules enter those channels, inside those channel walls is a set of turning vanes. So we take effort inside the channel wall to get decent distribution of that air up and down that vertical axis. And the same is true amongst the return air. So before those air streams come into contact with each other, we've taken measures to create uniformity inside that box. Then when those air streams and the proximity of those channel air streams come into contact with each other as they exit the damper blade assembly, now we promote heat transfer, and then you can see that gradient. It's a much smoother profile downstream. The same is true on side entry units. I made the comment about the value proposition being stronger. And the reason for that is if you had an air blender or a static mixing device or whatever mixing unit you've got, that's going to require some sort of downstream suction length. For a side entry unit, typically we can get more footprint savings using this channel blender technology. And the other thing I'd point out is it's a much easier way to get that outdoor air, that ventilation, across the entire plenum, so we don't have to deal with stratification. Like I said, we're starting to get into applications where maybe temperature stratification isn't the concern, but more dehumidification. So this technology is being installed in hospitals in Texas, San Antonio, Florida, in various locations where uniformity is important. So what we've done here is we've got into applications where poor RH control has been exhibited into surgical rooms. And so to do that during hot summer months, especially on side entry units, if we could reduce the variability of moisture or water going to that coil, they would have better operation. So what we've learned is that if we can raise that inlet suction temperature to the chiller by 1 degree Fahrenheit, that adds 3% efficiency gain to that chiller. So we're trying to quantify in dollars and cents, what does that mean for some of our clients? So we're continuing to work on that value proposition. Every one of our channel blenders are subject to CFD. And the reason for that is we want to provide our clients the surety and the data to know that freestat alarms can be eliminated during operations during cold weather events. So that's what we're after, and that's what we design around. Typically, we get asked the question, hey, how short can I make the mixing box, or where can I remove length from this air handler? And typically the governing variable inside the mixing box with the channel blender is not so much doing our work of raising the minimum temperature, but that governing variable is typically how much space do you need to remove filters in between the channel blender and that downstream section. For us to do our work, we typically need around 8 to 12 inches downstream of that blade. In terms of pressure drop, we'll see a bookend from around 0.3 to 0.6 inches of water column. This is a scorecard for the channel blenders we've built to date. We've manufactured and delivered about 350 of these channel blenders into operating units across the country. And these are some of the orientations. I would encourage you, if you come across an application or a retrofit unit that's kind of problematic, please reach out to Long or any of those sales application engineers, and they can look at the design of that channel blender module with you. This is a case study that was really twofold. This is a unit that was retrofitted in Albany, New York. The reason for the retrofit was they were having poor RH control into a downstream surgical room, into that space. And during the winter season, they were getting freestat alarms, nuisance freestat alarms on these units. What you're looking at is a unit on top of a rooftop that was installed in 2009. They did a series of field retrofits that included baffle plates, perf plates. When we showed up in 2019, there was a steel beam that was installed from the floor to the ceiling. And if you can imagine, there was 4 large industrial fans mounted on that steel beam. And the idea was, can we take the outdoor air that enters from the side and blow it across the plenum so it can effectively mix with that return air coming from the back wall? At the end of the day, none of those field retrofits were the optimal solution for them, and they continued to have operational issues. So they retrofitted this with a channel blender technology. The plot on the right basically is a plot showing extended economizing operations. So we've added over 2,000 hours of economizing hours. That's essentially free cooling. They keep those preheat circuits off. That saves on their utility bill. But the point being is we went through multiple winter seasons and we've had 0 freestats in that unit. And we've retrofitted 3 other units on this rooftop. So now that is a basis of design for their units going forward. At the end of the day, we recognize that dollars and cents matter. So what you look there as a plot where if you do the accounting, if you look at, if you could keep the compressor off and those circuits of preheat and cooling off, and if you look at the added additional energy penalty from a channel blender pressure drop, in cold weather climates, you're obviously, it's intuitive, you're going to get the quickest payback or the largest amount of annual operating savings. That's a plot looking at the savings as a function of blended electricity rates. So that includes the demand charge plus the consumption of kWh. Typically in Denver, for the clients we're working with, we're seeing for our C&I clients, the commercial and industrial, anywhere from 0.07 to 0.1. But the point being is there's over $10,000 of annual savings on a unit that's 44,000 CFM with 25% outdoor air. So as utility costs are rising, people are starting to look at, where some savings there. There's also some sustainability goals with, can we reduce peak demand? All these sorts of things are coming into play. But the payback for this type of technology, what we're seeing is in colder climates, we can be less than 1 year. Depending on your electricity rate, it can be even better. Now, I would also like to point out that these figures do not include any costs associated with responding to a freestyle alarm at 2 o'clock in the morning. So there's other things that can go into this. Please reach out to Long if you have any questions. We'd love to work with you to do a value analysis around this and look at potential retrofit applications. So with that, Bill, I'd like to pass the baton back to you, and thanks again for the opportunity.
Thank you again, Travis, and thank you everyone for joining us. We really appreciate your time today. Next week's topic will be advancements in indoor air quality technology, including bipolar ionization. We'll have Glenn Gabbert from Atmos Air with us, along with Mike Jacobs with Long Billing Technologies. Thank you, everyone. Have a great day. We'll see you next week.